Hello and welcome. In this video, we're going to take a look at the fundamental theorem of calculus. Well, with a title like that, you'd figure it'd be pretty important, right? Well, it takes together differential calculus on one side, where we're looking at derivatives and rates of change, and it puts together integral calculus, which, in our current interpretation of that might be just thinking about area under a function. Put those two pieces together, and we start taking a look at how we interpret the rate of change of area under a curve. And that is going to put all the pieces in place so that we can take a look at how to integrate a function by using rules of derivatives in sort of a backwards way. So let's start off with this idea. Let's let area under the function be, something we can represent in terms of x, like a function. So let's suppose that the area under a function f from a to arbitrary x, where x is anything in between the interval endpoints a and b, let's say that that's a function of x. So in other words, let's say the function g of x is equal to the definite integral from a to some point x of f of t dt. And this might be a little confusing. Why did we just suddenly throw t in there? We tend to use x, but well, we're letting x be a value on the horizontal axis, so we can label the axis with t, and we're going to say that we're going to take the area from t equals a to t equals x. We don't want to use the x-axis because it doesn't make a lot of sense to say we're looking at the area from x equals a to x equals x. X equals x isn't really much of an equation. So we have a picture in mind. If we take a function y equals f of t, we can graph that with the y and t axes, and we have our endpoints from the interval a and b being a comma f of a and b comma f of b. And what we're going to do is we're just going to take the area from a up to some value x. So we can put x somewhere in the middle. And then taking a look at the point there, this would be the point x comma f of x. And the area that we should shade in is going to be area from a up to x. Well, look at that. I managed to mostly shade inside the lines here. Now, I also have Desmos open here, so I can kind of show you an example of a function. Over here on my other screen, you can see I have Desmos open, and I have the function with f of x equals x squared. And you can see I've got this definite integral from a to b, and right now they're both set to 0. Let's leave a at 0 and see how, as we increase b, you can see area start to increase. So adjusting the slider from b here, you can see that the area is equal to 0, and then it starts increasing as we go. And I've got the area shading in here. And I don't know, maybe we want to look at the definite integral as far as x equals 2. Okay, so the interval from 0 to 2, total area is 2.66. And that's not really what I'm looking at of importance here. The theorem we're talking about is how quickly this is growing. You can see it's very slowly increasing area. But if we get as far as 1, the area starts to suddenly grow a little quicker, and it grows very quickly after that. So we can talk about how that number here is growing and how quickly it's growing. That is what we're really interested in with the fundamental theorem of calculus. So this number here is our g of x in a way, except I'm using b since, well, on Desmos I've already called this a function of x. So yeah, I've got b as a number here that on my slider. That's basically my variable. A is remaining constant, and I'm looking at how this number is changing with respect to the variable in this graph window as being b. All right, back to the concepts here on the notes. To think about a small change first, why don't we just simply take our value from a to x, and we're going to say since x is our variable here, we're going to just change x to be a little bit bigger or a little smaller by a small step h. H could be positive or negative, but let's make it very small. Estimate the rate of change of g. Well, this would be g of x plus h now. And that's going to be equal to the definite integral of f of t dt from a to x plus h now. And graphically, that's just changing x to be a small step left or right. Let's assume maybe we want to take a small step to the right. Here's my x plus h. Here's the point on my graph. And I'm certainly getting more area if I'm letting h be a very tiny positive number. I've suddenly increased area. Or if h was a tiny negative number, I've slightly decreased area. What we want to know is how quickly it's growing by. Looking at this green shaded area, we could represent that as being the difference of g of x plus h minus g of x. G of x plus h minus g of x is the difference of two integral functions. The definite integral of f of t from a to x plus h, and the definite integral of f of t from just a to x. Now again, I'm going to take a look at Desmos here and kind of give a visual representation of that as well. Let me just switch screens, and you can see I've also got a slider here for h. Now I'm just going to take a small step to the right by h, and you can see that small increase in area. Or if I let h be a small negative number, a small decrease in area. That is essentially what we're looking at here, a small step forward. And that could be for whatever value of x we want. We're just going to take a look, no matter where x is, just take a small step forward and see if we can estimate the change in area. We're estimating this little shape here, which is pretty close to a rectangle, except it's just got this tiny little slanted top. But since it's so close to a rectangle, that gives us a pretty good estimate. So back to the notes. Let's see if we can give an expression for an estimate of this change in area. As long as h is very small, then this change in area is approximately equal to the area of a rectangle with a width of just that little change from x to x plus h, which would be h. And the height, well, that might be a little bit trickier. Well, you can see that on this little graph I've drawn here, the height is really either of those red or green dotted lines. Why don't we just use maybe this like left endpoint, which could be the right endpoint if h is negative, but why don't we just use f of x as being pretty close to the height of that rectangle, since the height of f of x plus h is pretty close to the height of f of x anyways. As long as h is very small, f of x plus h and f of x should be nearly identical. Well, so long as f of x is continuous, and that is going to be something that we will see in our final statement of the fundamental theorem of calculus. So we can use the approximately equal to symbol and say g of x plus h minus g of x is approximately equal to width and height multiplied together, f of x for height and h for width. We could rewrite that in a way that might start looking a little familiar. G of x plus h minus g of x, the change in area, if we divide by the width h, that is approximately equal to f of x, so long as h is very, very small. And it may be just kind of intuitively, as h gets smaller, this gets to be closer and closer until we can use an equal sign when we actually use the limit as h goes to 0. Suddenly, this just jumps out at us. This is the derivative of g of x. This is the instantaneous rate of change of area under the curve is equal to the height of the curve at x. Maybe we should write this out in its integral form. And this might make it a little bit more obvious as to the interpretation. The rate of change with respect to x of the area under the function f from a to x is simply equal to the height at x currently. You can see here on Desmos, I've just reset h to 0, and I've got really just the definite integral from 0 to 0.5 right now. And that gets you a pretty tiny number. It's not a lot of area. But as I increase b, you can see that this is going to be slowly increasing at first. And when I get to b equals 1, you can see I've got a third. That's my total area. Now, if I plug 1 into the function, I get 1. So the rate of growth of this area right now is equal to 1. That's the instantaneous rate of change. So by increasing from 1 to 1.02 here, you can see my area has increased by roughly 0.02. Kind of like you can see that rate of growth of 1 exactly. If I look at the area from 0 to 2, I have 2 2/3. But if I think about the rate of growth at that point, by plugging 2 into the function, I have 4. See that, the 0.2 comma 4. So by increasing to 2.01, you can see that that area has increased by about 0.04. Again, that instantaneous rate of growth. However high up my function is, so here at x equals 3, this is now going to be at 9, which is actually kind of interesting as the area is also 9. Well, by plugging 3 in, my value of 9, that means that if I increase to 3.01, yeah, you can see it's about 9.09. The rate of growth of the red area is equal to the function evaluated at x. And it's always been kind of hard to envision this without maybe the aid of a computer. That really does help quite a lot. You have to be able to see how as I'm dragging that bar across, you can see the rate of growth of the areas is equal to the function evaluated at that value x, or in this graph here, you see it as b. Oh, that's part one of the fundamental theorem of calculus. Fundamental theorem of calculus part one states that if f is continuous on the closed interval from a to b, then by letting g of x equal the definite integral from a to x of the function f of t dt, where x is some number between a and b, that is also continuous on the closed interval from a to b. It's differentiable on the open interval from a to b, and the derivative of that integral function is simply f of x. It's really a nice way of saying that the derivative and the integral are inverses of each other, and they cancel each other out under these conditions where f is continuous. Now, with that theory completed, the fundamental theorem of calculus part 2, knowing how this differentiation and integration relationship holds, we can actually use antiderivatives as a way to evaluate integrals. Knowing that g of x has the derivative equal to f of x, let's say capital F of x is an antiderivative of f of x. In other words, capital F prime of x equals our function f of x. From the fundamental theorem of calculus part 1, we know that g prime is equal to f. So g is an antiderivative of f, and that means that g of x is equal to capital F of x, an antiderivative of f, plus an arbitrary constant. Let's put the integral function back in there, and that means that the definite integral of f from a to x must be equal to an antiderivative of f plus a constant. And we have a couple properties of definite integrals that we can use in order to solve for that constant. We know that if x equals a, then we have the definite integral from a to a of the function f. That equals 0. There's no area. Since this is g of a equal to 0, that means that f of a plus c must be equal to 0. Since f of a plus c equals 0, we know that c, this arbitrary constant, c must equal negative f of a. We can take that and plug that back into our expression of g of x. Now, what if we wanted to let x be the other endpoint and we let x equal b? Well, then that would be the area under the function f from a to b, and that would be capital F of b minus capital F of a. It's finding an antiderivative that's a little bit tricky, but it means that we can find the definite integral of a function over the whole interval from a to b simply by taking an antiderivative of f and plugging in the endpoints and subtracting. And that's going to give us our fundamental theorem of calculus part 2. Once again, we have this condition. If f is continuous on the closed interval from a to b, then the definite integral of f from a to b is equal to an antiderivative capital F evaluated at b minus the antiderivative evaluated at a. And it can be any antiderivative. You notice how we've changed our f of t dt to f of x dx? That's another property of definite integrals. Regardless of how we name the horizontal axis, we can still say the area or the meaning of the definite integral is the same. So now that we're not using x as being one of the endpoints of our interval, it makes a lot more sense to just go ahead and rename our horizontal axis x again. Now, a little notation for this. The difference f of b minus f of a is going to come up a lot, and sometimes it helps to show a few steps along the process where we need to maybe find the antiderivative first before we start plugging in a's and b's. So we represent this as the little notation, capital F of x evaluated from x equals a to x equals b. That means we need to find the antiderivative f of x, and then in our next step, we're going to plug in our b, and we're going to plug in our a into this function and subtract and find the difference. And that notation could be really helpful in this next example. Let's start off with that example that I have in Desmos right now, which is the function y equals x squared, or f of x equals x squared. Well, if we're letting f of x equal x squared, in order to evaluate the definite integral without needing limits as n goes to infinity and summations from I equals 1 to n and all that, we just need to figure out what an antiderivative is. And that's using our idea where we need to raise the power by 1 and divide. Now, notice that the fundamental theorem of calculus part 2 says any antiderivative. So I could put plus c on there, or plus 5, or plus 9, or just plus 0. And let's just choose the easiest option, letting it equal 0. So using this handy notation, I will just say that this is going to be equal to the antiderivative x cubed over 3 evaluated over the interval from 1 to 3. But now I can evaluate that by plugging in the endpoints. Plugging in 3 and 1 and then simplifying. 9 minus 1/3, which gives 26 over 3. Now let's take a look at Desmos. Here you can see I've got that same graph again, and I've got my b at 3, but a is still at 0. So let me actually just go ahead and change a to be equal to 1. Drag that slider up here a little bit and let that equal 1. And sure enough, 8.6 repeating, which is the same as 26 over 3. And visually, this is our area. But what we did is we actually used the antiderivative of x squared to evaluate this area instead of approximating it with rectangles. Okay, let's go for another example. Now this would be an otherwise difficult integral to try to use our definition with limits and sigma notation, but we might be able to remember an antiderivative of the function 1 over 1 plus x squared. Might need to stretch the memory back a little bit, but think of a function that has a derivative equal to 1 over 1 plus x squared. And it might come to mind arctangent of x. And again, I can choose any antiderivative, so plus 1, plus 6, minus 4, or just simply just plus 0, and let's choose the easy option. So using this notation, I need to evaluate arctangent of x from 1 to root 3. And luckily, these are some special triangles. Arctangent of root 3 means my opposite over adjacent needs to have a ratio of root 3 over 1, and that would give us the angle pi over 3. And arctangent of 1 means that I have to have a ratio of opposite to adjacent of 1 over 1, and that'll give me the angle pi over 4. And pi over 3 minus pi over 4 gives pi over 12. Now remember, it is possible to get a negative value out of this, especially when our functions are dipping below the x-axis. And going back to the definition of the definite integral in terms of Riemann sums and limits as n goes to infinity, we know that f of xi star, that can anytime be negative, in which case we'd be adding a lot of negative values to get the area. And so don't worry if this number is even 0 or negative values, any of that can be possible depending on the graph of the function. Now let's take a look and see what this looks like in Desmos. You can see here I've got the function 1 over 1 plus x squared, and I'm finding the definite integral from a equals 1 to b equals root 3, which is approximately 1.732, and I get the area 0.2618-ish. And again, that's just the same as pi over 12. Now, the thing I told you where you can use any antiderivative, that might be obvious if you take a look back here at this work, and you can see since I'm doing f of b minus f of a, if there were any additional constant in there, going back to one of these examples, well then I'd have 3 cubed over 3 plus 1 minus 1 cubed over 3 minus 1, and the plus 1 and minus 1 would simply just cancel each other out. Any constant that you have is going to cancel when you subtract f of b minus f of a, so they cancel out. And there we go. That's going to give us a brand new way to find definite integrals from a to b. And it's just finding antiderivatives and plugging in the endpoints. And it sounds pretty good right now. Unfortunately, the process of finding antiderivatives is not always straightforward. It's oftentimes much more difficult than finding derivatives. And that might not be great news, because sometimes finding derivatives is not easy either. But it's kind of like any sort of inverse process. If you learn how to square a number, then you're probably pretty set. You can kind of do that even with some really gross numbers, even by hand. But imagine just having to square root numbers without the aid of a calculator. Obviously, square rooting got a lot harder than squaring a number. And the same thing is true with finding antiderivatives and integrating. It can be a lot more challenging than our product and quotient and chain rules that we've learned for derivatives. So we'll look at that in the future. Thanks for watching, and I'll see you in the next video.